Okay, let's go to the afternoon session. We will start with Denise Gonçalves from the Federal University of Rio de Janeiro. She's going to speak about innovating the hunter techniques, the RAMSES 2, RAMan search for extragalactic symbiotic stars.
Good afternoon. Thanks for being here. And well, thanks for the opportunity of being here. That's a great meeting so far. And for me, it's a privilege being here to talk about a innovative technique to find the symbiotic systems in the local universe and in the nearby galaxies. Using this RAMan emission line that I'll try to explain you what it is about. The collaborators in this project are a number of people, and this part here are those that are really members of the RAMSES 2 team. So people in the different countries of the Gemini consortium. And here it's people, and one is in this too, that participated in something that I call the pilot project for this, that it was an attempt to use the Force 2 at the VLT to do the same science, but it didn't work quite well, and they will explain you why. So these guys we're talking about here are evolved stars, so in binary systems, we need to have a white dwarf accreting or a giant star. So a fraction of the wind of the mass of the giant star, it's captured by the white dwarf. And here it's a really beautiful example of this, because in this kind of systems, we have, in addition of the binary systems with these two guys in the center, we have this like a planetary nebulae like nebulae. And here we have this wonderful example. We see the jets that are coming out from this system. And in this case, using ALMA data and CO and continuum, it was possible really to take the position of the two stars in the system. So this is really cool, but it's the only example we see things so clearly. The fact that they have these binary systems has to do with this beautiful nebulae around the system. And because of that, there are the interaction between these two stars leads to a number of interesting physics for us to study, like the shaping of the nebulae, the accretion disk that it's there, the formation of jets, the peculiar chemistry of the stars because they have mass being transferred from one to another of the systems. And in addition of this, it's very much important as well that symbiotic systems are one of the really promising systems as progenitors of supernova one-way, on which here there are a number of possibilities for that. It's still not proven that they were the progenitors, but there are two ways that symbiotic systems can be related with this, using the single white dwarf scenario or the double white dwarf scenario, because in these systems we have one white dwarf and one giant star, and much later in the evolution, even two white dwarfs. So they are, really promising candidates as with the mass transfer. And to the white dwarf, we can reach the Chandrasekhar mass and then have an explosion of this kind of supernova one way. So these are reasons why we want to counter and mapping these kind of objects in different galaxies. And here I'm showing you the number of these systems we know in dwarf galaxies of the local group, and some of them. And note that for our own galaxy, the expected number is something between 3,000 to 424, but we only know less than 300 systems. And the extragalactic ones only 74, most of them in the much bigger galaxies like Andromeda or M33, and we are, studying this population in these dwarf galaxies. Even though I would say that you don't know how to estimate the number of these stars. We see that whatever is the way, if this is true or not, we really have only handful of these guys in the local group coming from dwarf galaxies. Another thing that is important, I don't have time to go through all of these, but it's important to remember that this kind of systems will appear in the dwarf spheroids or irregulars, because they are, as much as planetary nebulae, present in the quiescent or star-forming galaxies. So you can really go for a number of, most of the dwarf galaxies in the local universe. Traditionally, the way of finding these guys is using color diagram, and on which, if, for instance, you have here a IFAS example, so using the optical, the R minus I band versus the R minus H alpha in the located stars there. But this is not enough, because there are a number of other emission line stars that would appear here as well. Then you can use as well the infrared to try to much better select these objects, even though this is a much older version. And if you go here, and it's 2 mass as well, but in this much nearer example, we see that there are a number. Here it's the place on which you see the symbiotic stars. But you see that there are a number of other objects that would appear here as well, like planetary nebulae, B stars, or CVs, young stellar objects. So after using these kind of things, you need the spectroscopic follow-up. In fact, this is the kind of work that it's being done by M33 and M31. A number of objects were detected in this way. And I would call attention here very quickly to, that you can use color diagrams much better than those I was talking about just a minute ago. For instance, you use the J and the S plus that Vinny Placo explained to you this morning. Because here we have, in addition of the broadbands, we also have a number of narrowband filters that would make a much better job in terms of selecting the objects in the optical. Using those two systems of filters, what we're putting here are kind of word colors, because these are colors of the J and S plus system, photometric system. And here, wherever that it's in red, are symbiotic systems. So here we do a little bit much better work than using the traditional ways of finding these guys, or finding by the candidates of symbiotic stars using the optical. But then, of course, as in the previous slides I show you, the follow-up, the spectroscopic follow-up is mandatory in this kind of work. Then what we are doing with the RAMSES 2, our approach is we want to map this population in dwarf galaxies of different mass and metallicities. But we want to do this using a purely photometric technique. And this is really important because, for instance, if you think of mapping this population in the nearby galaxies, if you take the SMC, for instance, the expected number there, it's this number. So far, only 12. But then we are not doing this exactly in the SMC because SMC is too huge, so you would need to observe SMC forever to be able to see the population. Then we are doing with the smaller galaxies, in fact. But what's the way you are trying to do this without using the spectroscopy? The fact is that there is an emission line that it's unique of this kind of system, that it's this RAMan emission line, that it's the scatter of the O6 line in the UV, that it's, these are resonance lines, they are scattered by a huge column density of neutral hydrogen. And this is the kind of configuration that it's unique of these systems. because you have the white dwarf that is responsible mainly, not only, but for the O6 emissions, so the higher ionized gas, and as well as a huge condensate of neutral hydrogen coming from the giant that, matter it's being accreted to the white dwarf. So this is really, it's really unique of this kind of system. So if we see this emission, we know for sure we're talking about symbiotic systems and not other kind of emission lines or emission line objects. Using that, this pilot project I mentioned before, we select at the SMC a number of candidates, and they did this using a sulfur 2 filter that it was meant for high redshift galaxies. And then because of that, we had I'm with problem here, sorry. I can help you. No?
Did it turn off? Yeah.
And move too much, so it's okay. I tried not to move much. The point is that you use those filters at the VLT and in order to pick up this emission. And then you had 12 candidates, and then you went for the spectroscopic confirmation, and they turn out of being false positive O6 emitters. And why? So here is the spectra you took for those guys, or they are here. And the reason, what the important thing here, these are the spectra of, cold stars, giants, red giants. And the reason is that the filters, the pair of filters we were using were not really appropriated for this emission. Okay, the point is that the continuum of this kind of objects can be, this one is really a well-behaved one. But there are a number of characteristics of the cold stars here that make the work not that easy, only using 2 filters and not really appropriated, because you see here we are summing this and this, so it's hard to see the emission of those 6. Then what we are doing now, the RAMSES team is doing, is like imaging. So here it's example of the one galactic symbiotic system, and well, you see the whole spectrum here. And what we're doing now is, in addition of proving the O6 that could be false because of the kind of because of the spectrum is not flat in that part, we are also measuring the emission in helium-2, because the ionization potential of the O6 is twice as much as the helium-2. So if that guy is that emission is present in the system, this one will be there as well. So we are imaging using narrow band imaging here, and it continue. H alpha as well, of course, whatever ionized gas you have H alpha, and then a filter centered in the O6 line, the RAMan O6 line. Okay. This way, what we're doing is like trying to be sure that we have the O6 in this red part of the spectrum, and all the and signatures of the ionized gas as well, H alpha and O6. For that, we really need proper filters to do that. So the team built O6 and the O6 continuum filters for the GMOS in the north and in the south. And these filters are here. And we have the on-band filter and the off-band one. That's here are the characteristics of these filters. And here we see, just to be very clear, that the continuum and the region of these lines is very, can be met. So this is why you need to get imaging in not only this pair of filters, but the other 2 as well. It's important to remember that Gemini sponsored these filters, and well, they were successfully proved a while ago. So here are the results of the first results we have in the science verification phase of the project. They were published in this paper you see here. And this is the field of view of Gemini, and this is Gemini South. And we choose a object that we knew for sure that had this O6 emission. And we see it there. So O6 minus continuum, you see the guy there. This is not a crowded field. Then in a crowded field, as you see here, again, we have a guy that you knew that were emitting this O6, and you see there the emission clearly. Then we have a third one here, only to know that this guy is as well an emitter of the O6, and they didn't find it there. And why? So, in the following day of these observations, this image, we got a spectra, and you see that the RAMSES here, the emission here, very faint. In fact, for this same guy, we see from the 2013 to 2017, we see that this emission is fading. So we have a limit. You need to go really deep to be able to see this line in the faint object. And then there was a very nice surprise that is this guy here, MC1, that so far is not a RAMan emitter, and then we find this. Because of that, we got the spectra in the following light, and you see here the emission. And this is the comparison in 94, that there were no emission of this, because this emission is varies with time. So all in all, there are lots of things here, but the important thing is saying that this emission line is almost unique of symbiotic systems. So this is why we are using this one to map this population. The other thing is that there are some other, mainly young planetary nebula, some like dubious ones, like this one, that show lines that could be identified as this one as well, but well, it's not for sure. So the point is that only half of the population, if you put together the galactic and the extragalactic guys, only half of the population would find at a certain time, show at a certain time this emission. So it's not that they can, using this way, find all the symbiotic systems in a galaxy. You could find at most half, but then you double this number, you know the general thing. Another limitation is that you are seeing here in nearby dwarf galaxies, these two guys, we see that the emission is very faint. So you need to go deep to see this. In fact, the luminosity in this line goes with the luminosity of the system. But anyway, if you put all the different guys together, this emission is about 5% of the HR emission in the system. So, but there is the advantage that this is a broad line in general because of the scattering field, and then it's much easier to observe it, even though it's faint in general. So what we did, we observed in the 6 filters all these 4 galaxies. These are all dwarf galaxies in the local group, and you see preliminary results for 4 nights in a poster being presented by Rodolfo Angeloni. Tomorrow we'll talk about it. And then I will show you real quickly the results for this guy here, and then we have another 2 to analyze. And it's important to show here that you are using these 4 galaxies, you are proving different metallicities, because so far you don't know what's the effect of the metallicity on this kind of emission. The result here is that for this galaxy, we already knew 1 true symbiotic system and another 2 that are possible. But in that work that it was meant for planetary nebulae, we observed 2 fields, and this time we have only 1 field. And here it's the exposure times we use an on and off band of these 3 units. And here is the result. So the first thing, we recover in the sequence here, it's not written, but this is H alpha, helium 2 and O6 emission of the guy we know. no, the 3 bands. And this is only the 8th emission, that one that's a possible planet, possible symbiotic system. The helium-2 we were not able to recover, but it's really, really much fainter than the other. And then we have 4 new systems that are these 4 here, which is simply the emission in H alpha. I mean, this is the on minus minus off band on band and off band emission, and then you see this. So the emission H alpha in helium-2 and O6 for this system. So in this case, we know for sure this is a symbiotic system. Yeah, if you do simple extrapolations here in terms of estimating the number of this kind of objects in this galaxy, you would have, when comparing that estimation I showed at the very beginning, again around 2003, with we are doing now. So we take this one field and the galaxy in the result of that, and then you need to understand that you have much more, twice as much, and you are only observing part of the galaxy. So the expected number in this galaxy would be this one. The conclusion is of this is that we really don't know how to estimate this population, neither in the galaxy or in any other galaxy. So we are trying our best. And as the last one, the important things here is that so far the symbiotic systems that we know in this dwarf galaxy of the local group work only via serendipitous discoveries. With RAMSES 2, the project is designed to do these statistics in this kind of galaxy in the local group. We built the filters, the proper filters to do this, in Gemini South and Gemini North that are attached to GIMOS. And for this galaxy in particular, the number of systems went from 1 to 5. So I think that we already, proven that it's a promising way of mapping the symbiotic systems in the local group. Thank you.
Thank you. Okay, we have time for a couple of questions. Is there any question in the audience or Slack? No? I would like to encourage students to make questions. Yes, this is a very friendly environment, so it doesn't matter if how basic your question you think it is or the level of your English. Please don't be shy. This is a very good opportunity for you to practice how to
We have
interact.
one on the Slack. I can read
Yeah.
it. There's nerdy data reduction question. So how do you PSF, how do you do the PSF matching when subtracting the narrowband image from the continuum image?
This was really the complicated thing in this project because, for the first observations in this galaxy, in fact, you don't have like the ideal thing, and you need to observe the sequences one after the other in a very particular way, not to be able to do not have that much of shading, syncing, and sync for one to another of the image. So this is the work that German is the work that Germany of the Gemini is doing, because we tried a number of different ways. For instance, if you use the photometer for crowd fields and try to do it automatically, it does not work. So the way you do is treating and retreating this image, all the the combined image to find these guys using PSF matching. Yeah, no other way. The other for one you use anyway.
Any other question? Okay.
Nice talk.
Thank
So
you.
let's see, maybe a dozen years ago, late 2000s, there were lots of people, well, some groups of people trying to make binary population synthesis models. The folks who make BPAS, and back in the 2010s, everyone just kind of wanted to ignore them because it just made population synthesis so much more complicated. because of all the additional parameters. But they persisted, and when first LIGO results came out, all their work was cited. So I was just wondering, it's kind of a high level question, but the survey like this, how does that inform the parameters that go into, or the models, the binary population synthesis models?
Yeah, I mean, there are two things. The first thing, I mean, the very easy thing on our side is that as this population is not known in the nearby universe, you try to map this. And this is the first thing, and it's important in itself because of the physics behind this kind of object. The other things that so far we don't know how to estimate this, because in fact I have a student that it's doing this work, like following the evolution of the two stars in the system, not theoretically speaking, and there are a number of channels or different ways to end up with these systems at a certain epoch in the evolution of these two stars. And then the point is that when you are able to do this from the theoretical side or modeling and from the observation, comparing these two things, you'll be able to say something more. So far, you don't know even the effect of metallicity on this. You only know part of the population in the galaxy. So it's so kind of really in the first steps of this science. And it's not easy because not even, for instance, knowing the fraction of binaries at this mass range per galaxy, it's something that you know for sure. So yeah, it's a long way to go.